Thank you for the introduction, and thank you to the organizer for having me there and inviting me to give this talk. So I will first have to say that what Martin just said is not totally correct. I won't tell you everything about this, because it would definitely take more than 1 hour if I did so, but I hope to tell you enough so that you understand why it's important to understand these extensions, and also what kind of results we can expect. So maybe I should start by telling you why I'm studying this. So here is kind of the third talk in which you see, let's say, representations of our Hecke algebras in characteristic P. So the first one was yesterday by Guignard, and he discussed about mod P representation theory of p-adic groups. This morning you had characteristic P representations of finite groups. And tonight you'll have Iwahori-Hecke models in characteristic P. And all these things are related because my main motivation here is to understand the smooth. So I will put this admissibility condition here. The smooth admissible representations of SL2F over an algebraically closed field of characteristic P. So the same P for F. So F is, as in all the talks we had so far, F is either a finite extension of QP or a field of Laurent series. In a finite field, in a finite extension of Fp. Okay, and P is a fixed prime number. Okay. So I hope, and I think that yesterday through Guy's talk, you've understood that understanding this mod P representation theory is something really hard. Maybe I would like to insist a bit more on this by saying that so far, there are only 3 groups for which we understand all the irreducible smooth representation. It's GL2QP, SL2QP, and the unitary groups of signature 1,1 defined over an unramified extension of QP. Otherly said, if I take a non-trivial extension here, either for GL2 or for SL2, we don't really understand the irreducible smooth representations because we don't understand the supercuspidal one. And the idea of using these Iwahori-Hecke models here is to try to use the specific features of the characteristic P to get a hand on the representation. So in particular, let me recall that yesterday we've seen that if P, so curly P, is a pro-p group, and if V is a smooth non-zero representation of P over this algebraically closed field of characteristic P, then it always have non-zero fixed invariant. And the point here is to remark that the space of p-invariant vectors can be seen as a home space, namely the space of p-equivariant morphism from the trivial representation, so this is a trivial representation, with value in V. And then you're using this Frobenius reciprocity to say that this is canonically isomorphic to the home of G equivariant representation of the compactly induced representation of the trivial character from P to G with value in V. And I mean, the usual thing we've seen during the last 2.5 days is that this is endowed with an action of the endomorphism algebra of this compactly induced representation, which is a Hecke algebra that I will denote by H, G, P1 to keep track of everything. Here, I mean, you can think, well, it's just a trivial character, but the thing is that I will need this notation further for other characters, so I want to keep a track on the character I'm inducing here. Okay? So finally, this is a non-zero model over this algebra, and the idea is to try to find reasonable p's for which, first one, we can understand very nicely this algebra here, its models, and secondly, such that we can hope to get some information over V using the p-invariant vector. So find suitable p such that we understand. So the category of right model over this algebra and kind of its relation with representation theory. Oh. So with the category of smooth representations, for instance. You will see in the cycle that I will have to be a bit careful here. Man. Okay. And the thing is that, in particular, there are kind of two instances of P's that are quite useful. So, two main examples. So here I will need a bit of notation, first part. So, as I said here, for me G will be SL2F. Usual notation, OF is the ring of integer. Like, so we have OF, and we have the residue field, KF. I think that I will not need any uniformizer, so I'm safe. So I have this G being SL2F, and inside you have this first congruent subgroup, just the matrices, with coefficient in OF that are congruent to the identity. Okay, I need the maximal ID. So this is, we've seen this in several talks, this is a pro-p radical, meaning the maximal normal pro-p subgroup of the group I will write here, just K, which is the integer rational points of SL2. So this is the first P we can take. And if we do so, what the kind of Hecke algebra we find here is those we've seen yesterday evening in Guy's talk. It's this spherical Hecke algebra. And the other option, so here basically what we do is that we are looking the stabilizer of a vertex in the tree of SL2. And the other option is to look at the fixator of an edge in this tree, and in this case we get this standard pro-p-Iwahori subgroup. So here, let me write it like this, all the elements of SL2OF that are mapped with via reduction mod, the maximal ideal, on upper unipotent matrices. So this is in SL2KEF. Okay, so it's just the matrices that are 1 something 0 1, and this is the pro-p radical of the Iwahori subgroup. Which corresponds to the matrices whose image under the mod P reduction is upper triangular. Okay. So if we take I1 to be P, then we recover what we saw in Maya's talk, but I mean, she was talking about C, but here we are over another C. It's a Iwahori-Hecke setting, Iwahori-Hecke algebras. And I really put an S here for a good reason. So this algebra here will be the pro-p-Iwahori-Hecke algebra, and it can be decomposed using Iwahori-Hecke algebras, as I will show you in a minute. Okay, so this is the setting you are interested in this talk. So what we want to understand is this algebra with having I1 here, its simple models, and the extension existing between them. Okay? Okay, I don't have this one anymore. No. So the talk will go as follows. The first part will be kind of a, let's say, crash course on the Iwahori-Hecke models, simple models, meaning the simple models over this algebra. Then the second part will be two necessary conditions to have non-trivial extensions. And then I will give you some instances of computation that can be done. And if time is allowed, I will compare these spaces with what happened for the corresponding representations. Meaning I will tell you what it means to look at the corresponding representations. Maybe I can say this here. Okay, so outline, maybe here. Okay, so the first part is just, maybe you should keep some space here, because there will be a second part and a third one. Okay, so the first thing to do before understanding what are the models of the algebra is to understand what is the algebra. And here we'll, okay, in Maya's talk, we've seen that these algebras have some nice description using by generators and relation using this extended while group. But here, I want to do this another way and using really this description as an endomorphism algebra and the fact that compact induction is transitive because it will make our life simpler when we will want to study the simple models. So this AG1, as I said, is just this endomorphism of this compactly induced representation. But using transitivity of compact induction, we can decide to make a stop via the standard Iwahori subgroup. So just say that this is the induction from I to J, or the induction from I1 to I, of the trivial character. And this is kind of nice, because this thing here is just a bunch of characters. So maybe I should have recalled you here that if you take the quotient of I by A1, it's like taking the quotient of this finite Borel, but it's unipotent radical. So we just have the finite torus, but we're in SL2, so this finite torus is just Kf star. So this is just the sum of the character of Kf star. Omega to the R is going from Kf star to Fp bar, and it's just taking an element and mapping it to its rth power. I mean, just a cyclic group of order q minus 1. So I take a generator and defining the character is just deciding on what I will map this thing. And here I should say that I fix an embedding. So from now on, C will be an algebraic closure of Kf, and I fix an embedding of Kf into its algebraic closure. This one I've chosen. And this is Yoda knot. Okay, but so here I'm saying this Yoda to really point out that I need to fix this embedding, but in the sequel I will just forget about it. And this KF cross here is really I mod I1. So I will denote the same way the character of this KF cross and the character of I obtained by inflation from this quotient of this character. Okay? So we have this, and now we can just say that this representation is just the sum of Q smaller induced representation, okay, from characters of the non-zero elements of the finite residue field. Okay, I mean, I think it's obvious for most of the people here, but maybe not to everyone. This doesn't mean that this Hecke algebra is directly the sum of the endomorphism of the thing here, because you have to be careful. There can be intertwining. Between components on this side. So on the right-hand side. Okay, and actually there are some, and they are coming from the fact that, so for SL2, the Weyl group is really small, it's just S2, 2 elements. But this Weyl group is acting on this finite torus, so on this thing, just by conjugacy. And here it's amounting to map R onto Q minus 1 minus R. So the thing is that you will have non-trivial homomorphism from this representation to the one having Q minus 1 minus R here. So you also have to take care about this hom. But there are two cases in which basically you don't do anything, is when R is equal to Q minus 1 minus R, meaning that either, okay, congruent mod Q minus 1 minus R. So basically if R is 0, or Q minus 1, it's just the same thing. And if R is Q minus 1 over 2, then it's a fixed point 2. So what you get from here, but consequence, kind of you just make some computations, what you get is that this Hecke algebra you're interested in can be decomposed. So there is a natural algebra is a homomorphism. So between this thing here and R equals 0 to Q minus 1 over 2. So I take the integer, the flow part of Q minus 1 over 2 of some algebras where, so H naught is just the Iwahori, the standard Iwahori-Hecke algebra. Okay, then H, when it makes sense, so HQ minus 1 minus 2 is, well, yes, the same thing, but for this character having orbit of size 1 under the action of the Weyl group, and then otherwise. HR will be a matrix algebra, and here you will have HGI omega R, HGI omega Q minus 1 minus R, and here you will have things which are explicit, but I will not need them, so I don't say, but it's just the hom from this one to Q minus 1 minus R and the reverse one, okay? Maybe a word. Okay, so this will correspond to what I will call in a second the Iwahori case, and I will say why. This corresponds to the so-called regular case, and this corresponds to the exceptional case. Okay. Okay. So that's the first thing. And maybe let me say today that I will not focus on this case. It's quite different by several aspects. And I think it's already interesting to have information there. And as I said, otherwise I won't have enough time to tell everything around. As we will see in a second, these two algebra look quite similar, but you will see that when it's about the model representation, the models of this algebra, it's very different. But in particular, maybe note, a simple HGI1 model will always come from a unique simple HR model. For a well-chosen R, okay? Okay, so this means that to understand the sample model of this big algebra here, we just have to understand what's going on the component. So this has been done several years ago, I mean my thesis, and we get a full classification of the simple HGI1 models. I will not give the classification explicitly here because it will take something like 3 blackboards and we will not need it. But what we need, some facts maybe. So the first thing that can be proved and kind of abstract nonsense is that every simple models on this algebra is finite dimensional. But what we got is that they are all 1 or 2-dimensional. So that's make life really easier. So all these models are of dimension 1 or 2 over fp1. Something else is that in the Iwahori, or in the exceptional case, the corresponding models will be kind of almost entirely characterized by their central characters. Okay. Well, and something else, maybe to relate this to the motivation I've told you earlier, is that we have natural bijection. So the first one is between non-supercuspidal irreducible smooth representation of G over F up to isomorphism and what we call non-supercuspidal, non-supersingular, and I will tell you what it means. HGI1 models. And the same thing holds for, maybe I will write this, all irreducible smooth representations, but when it's QP, and all this non-supercuspidal simple. Yeah. Models. And here just simple HGI1 models. But here we really need to have QP. And maybe it's something I can say also. There's a third, I mean, there are two extra bijections that analog with non-zero EI invariant vector. And HGI 1 modules. What I mean here is that if I just restrict here to representations that have non-zero E invariant vectors, I mean, it's definitely not automatical, that such representations have fixed vector under the Iwahori, not the pro-p, but the Iwahori. But if I just look at these representations here I can do the same thing, but by putting I instead of I1. Let me also say that here, this bijection actually comes from an equivalence of category. This has been proved by Koziol for SL2QP. And this equivalence of category doesn't exist if I take F, but it doesn't matter. Yeah.
Can you explain maybe why a different field would be so much more difficult than QP there?
Oh, God. Well, there are several reasons. So here the thing, okay, first thing, so here I don't need anything about QP. I mean, on the Iwahori-Hecke side, I mean, what I'm telling you is really valid for any F, okay? Here there are several reasons. So first one, here, to have this bijection, we really use the fact that we know all this irreducible smooth representation, meaning we know the supercuspidal, okay? And the thing is that when F is not QP, we don't know the supercuspidal, and we know that they are far much more complicated. For instance, okay, let me say this for GL2, but it's working the same way for SL2, the fact that you also have this packet phenomenon. But for GL2, Schran has proved that if you take a supercuspidal representation of GL2F with F not QP, then the representation is not even a finite presentation. Yeah, that's something really ugly. If you think on this thing, what's happening is that you don't have, so here you just take a representation and map it on its I1 invariant. So to have this equivalence of category, you need to have something fully faithful. It's not fully faithful anymore when F is not QP. And the thing is that we don't really understand how things behave here. Something else, which is related to what I've said there, is that, so here we look at all the smooth representations, and this equivalence of category is not for all smooth representations. It's for the one generated by the I1 invariant. And this category is maybe not behaving as well as the big one. I mean, I can go on like this for half an hour, I think, so maybe that's not the point. But no, it's really, really different. Okay, so 1, 2, T3. Okay. Well, are there other questions when I'm lifting the blackboard? No? Okay. So maybe something which is also going wrong. So I think you've already heard this in the previous talk, but the thing is that when we're in characteristic P, so the category of smooth representation is definitely not semi-simple. And so, well, I mean, of course, this category of modulus over this algebra is not semi-simple neither. And if you really want to understand the full category, then you have to understand the extensions between the models. So the first step is, well, trying to understand the X1, and it's what I will talk about in the next part. So I call this two necessary condition. And some applications. Okay, so the question we addressed in the second part is the following one. Given two simple H1, okay, let me write this H1, okay? models. Okay, there are 3 sub-questions. When do we have the non-vanishing of the x1? And can we compute its dimension when non-zero? Maybe I will just say, can we describe it? At least as a vector space. Can we describe this vector space? Okay, and so here, I will just give 2 necessary conditions to have the non-vanishing of this x1, and in the third part, I will describe this x1 in some instances I've mentioned here. Okay. So the fun thing here is that the 2 conditions I will give you are kind of really elementary conditions, but you can already do a lot of things with them. So the first thing you have to note, I will just put fact because it's really just something you observe. So here we have this decomposition of H1. And the thing is that if M and N are living in 2 different cases, then if you take an extension between them, well, maybe I should say this first. Elements there, recall. Another element of this extension space can just be seen as a non-split short exact sequence. Correspond, maybe it's just a non-split short exact sequence. So Mn, so N is a sub-object here, and then we have something, and then we have M, and then we have 0, and it's in this category. Okay? Maybe assume P is not 2 here, but 1. Okay, so saying that this space is non-zero amounts to say that there are non-split short exact sequences between these 2 models. And the thing is that so N and M are simple models here. So they are living on 1 component. I mean, there are HR models for a given R. And if there are models on different components, then you can't hope to have non-split extension between them, because just the extension will just be the direct sum, necessarily because of this. So the first fact is that if x1 h1 of mn is non-zero, then m and n must live on the same component. Meaning there are HR models, simple HR models for the same R. And just noticing this already has an interesting application about representation theory. So this application is an answer to a question that has been asked by Kohlhase. So the question is as follows. So Pascunas showed that there is a unique non-split short exact sequence between so you have the trivial character as a sub-object, and you have an irreducible parabolically induced representation. So here it will be iota r and iota -1 in this category of smooth representations. Okay, F is QP here, okay? And P is bigger than 5. Not because of me, because this proof only works if P is bigger than 5. So you have this non-split extension, I mean this non-trivial extension between this parabolically induced representation and this representation. And the thing that Cole has approved is that that this E is the so-called smooth dual. So I will not define here what it means. Okay, it's kind of the so far only reasonable duality you have when you work with mod P representation of the Steinberg representation. So the Steinberg, it's really just the quotient of in BG1, I1, as in yesterday's talk, okay? And the fact is that, so the question is E generated by its I1 invariant vector? Okay? So these questions come from the fact that this equivalence of category I've mentioned here, as I said when I answered to Martin's question, is an equivalence of category between this category of models and the category of the smooth representation that are generated by the I1 invariant. And the thing is that this Steinberg representation belongs to this category, this representation belongs to this category, and this one also. And the question is whether E is also in this category. And the answer is as often a negative answer. No. E is not generated by its I1 invariant vector. And the reason here is really as follows. So this short exact sequence, formally it's for GL2QP, but you can prove, because it's just non-supersingular thing here, that it stays non-split for SL2QP. So I can just assume I have SL2QP here. So in this context, assuming by contradiction that E is generated by its I1 invariant, would say, using this equivalence of category, that we have the same short exact sequence, but for the I1 invariant vectors. But now, the thing is that when looking here at how objects are mapped to each other, this model we have here, this I1 here, is in the Iwahori case, where this one here lives in the regular case, namely for R equals 2. So there can be non-split short exact sequence between this I1 invariance vector. So if you look on the level of I1 invariance vector, you have a split sequence. Another thing is that as all these two things are generated by the I1 invariant vector, having a splitting on the level of I1 invariance vectors gives you a splitting here if you assume that this one is generated by its I1 invariant. So it can't be generated by its I1 invariant. Okay? So that basically implies that the smooth duality doesn't preserve the category of representation that are generated by the I1 invariant. Okay? So the thing is that it's kind of, if you really try to work out this just using the representation theory, it's pretty hard. If you use Iwahori-Hecke methods, it's pretty easy. Okay. So that was the first elementary fact. And I have another elementary, I mean, maybe not that elementary, so I will call this a lemma. So again, M and R are simple models. And you can prove that if this extension space is non-zero, then M and N have the same central counter. And the thing is that in this setting, an immediate corollary, maybe corollary 1, I mean there's another one coming, is that if M is supersingular while N is not, then you can't have non-split extensions. Between these models, okay? And this thing, if you look at the corresponding statement in the representation theoretic setting, it's definitely not easy at all to prove whether it's true or not. For instance, for GL2QP, Pascal has proved that if you have a quotient which is supersingular, then necessarily the representation that appears as a subobject is also supersingular. But I mean, the reverse thing, meaning if we know that the subobject is supersingular, does the quotient necessarily be supersingular is not clear at all. Okay? So that's the first thing, and this comes from here because basically we know all the central characters, and this remark I've done here kind of allows you to check that in these two cases it's obvious, and in the regular case it's coming from just kind of by hand computation, checking that this central characters doesn't match neither. So maybe here, as I said, I said I will not care about the regular case today, so don't care about it. Okay. And another corollary coming from this thing here is that if, so again, in the Iwahori or exceptional case, if M and N doesn't have the same dimension, then there cannot be non-split extensions between them. So this one is really a fun fact, actually, because there is no reason at all why it should be true for the representations. And I think it won't be true for the representation. Okay. Okay, but here it's really in the Iwahori or exceptional case. Good. So we have two necessary conditions, and maybe in the 2 last minutes, example, Iwahori. Okay, I would like to talk about this one here, and exceptional cases. For one-dimensional models. Okay. Maybe I can just draw a board. So quickly. So H naught and HQ minus 1/2 are of the form. So you have two generators. I put brackets like this because T0 and T1 doesn't commute, okay? It's polynomial in these two operators, but they don't commute. And you have the usual quadratic and braid relations. So Ty square is epsilon I Ty, and T0, T1, T0 is T1, T0, T1, okay? And here, epsilon is 0 if you are in the exceptional case, and it's -1 if you're in the Iwahori case, okay? And the thing is that in the Iwahori case, you have four one-dimensional models. You have two supersingular model. Okay, maybe let me go. We have a parametrization like this. So it's one-dimensional characters, modules, with the epsilon i's being either 0 or -1. So there are 4 options. And in the exceptional case, you just have one-dimensional module, just an M star naught. Okay? So these are the one-dimensional models. Okay? And the thing is that okay, maybe I'll do it like this. So the thing is that the behavior of these extension spaces are really different, though the algebra are not that different. So here I will put the Iwahori case, and here I'll put the exceptional case. So first thing, we know that we can't mix up supersingular and non-supersingular thing. Here, being, maybe I can write this, being supersingular is saying that epsilon naught is not epsilon 1, and this one is supersingular. So, for instance, self-extensions. So can we have a non-trivial extension between a module and itself? In the Iwahori case, the answer is no. In the exceptional case, the answer is yes, and the space is two-dimensional. Okay, would I have a bit more time, I would explain to you how you prove this, because it's really not very difficult. When it's about crossed extension, like to take two different models, so here it doesn't make sense, because we just have one. And here the answer is yes, we have crossed extension, and all the spaces are one-dimensional. Okay? And, well, it would be interesting to see that, for instance, in the representation, the corresponding representation theoretical setting, here we have at least one-dimensional spaces, but sometimes it can be bigger. Here we have a non-trivial extension, but, well, it's not clear whether we can build another one that would correspond to this non-trivial extension for the Iwahori-Hecke modules. Okay, I apologize for the 5 extra minutes, and I thank you for your attention.
Okay, thank you. Other questions?
Give some reference.
For which part? So for the two first parts, this one here, kind of understanding the algebra and its models. So it's in my thesis and it's in a preprint. It's paper submitted, but still waiting for the acceptance, that you can find on the internet. And the third part is in preparation. So I said it's a work in progress. So all I've told to you today is proved and it's almost written, kind of almost ready to be submitted. And the part in progress is really about what's happening with two-dimensional models. And the thing is that for these models, I have to use kind of parabolic induction to make things go, let's say, less technical in some sense. So this part is not written yet, but, well, let me say, coming soon.
Further questions? Oh, maybe I have another question. Oh, let me use the microphone. So, all this looks like it's a lot of computations. I have difficulties seeing the method behind it. So I was wondering, is there also some way in which you can obtain this from representations over on ZP modules and then reducing modulo P?
Well, you have to be careful if you do this, because the thing, the thing is that if you're looking at ZP representations, then you're not sure a priori that they have I1 invariant vector. So you have to be careful about this. And if you really start from mod P already representations, the thing is that this I1 invariant functor is not an exact functor in general. It's just left exact. And the thing is that when you look at non-supercuspidal representation, irreducible ones, you can recover these extensions because you can prove that actually it's, well, most of the time exact. But when it comes about supercuspidal ones, then you can prove them, like in this example, you can build that kind of examples in which you cannot recover the extension by using the representation theory. So, the main interest of using this Iwahori-Hecke model is that, well, there is no problem to distinguish between F is QP or is not QP, and, well, everything is finite dimensional, you can really kind of, but there is, maybe I should say this, there is an analog of, for instance, this parabolic induction we've seen yesterday for models. Noriyuki Abe kind of proved, make an analog construction and proved that using the computation of Venera's showing, giving you the supersingular models, then you can have a full classification for any connected reductive group, for instance. And the thing is that this parabolic induction functor, it has good properties with respect to these X spaces. And it's the kind of thing you use, for instance, when you want to compute X spaces for higher dimensional models. But here, just one dimensional. So you just take my hand.
Okay, thank you.
You're welcome.
More questions? If not, let us thank the speaker again.
Thank you.